This recording will help you understand how you can use NUCAPS and Gridded NUCAPS in the forecast process. I'm Scott Lindstrom from SIMS. NUCAPS is an acronym, NOAA Unique Combined Atmospheric Processing System. If you want to know a little history, it was first the NOAA Unique CRIS ATMS processing system when it only looked at data from SUMI NPP or from NOAA 20. But then MEDOP with EASI and AMSU and MHS data were included in the NUCAPS processing. The SBN feed in your AWIPS only supplies NOAA 20 NUCAPS data. You can get SUMI NPP NUCAPS data from an LDM feed. There are plans to make that easier. With two satellites you get twice as much data, and there's a nice time separation between the two, 45 to 50 minutes, so you see how things evolve. One of the things that's difficult about polar orbiters is knowing when they're going to fly over you. You can find orbital paths online at this link. For SUMI NPP and NOAA 20, a typical day's passes are shown here. Flying along the east coast, you get something between 6 and 7Z, and then again between 17 and 18Z. NUCAPS combines CRIS data and ATMS data, so it's combining infrared data from the CRIS with microwave data from the ATMS. Data flows from NOAA 20 to Svalbard or McMurdo through a variety of computers to the WFO. This takes about 60 minutes for NOAA 20. This is a significant improvement over what it was for SUMI NPP, when the latency could be up to 2.5 hours. So if you're familiar with NUCAPS from SUMI NPP and you gave up because you were waiting too long, give it another try now with a 1-hour latency from NOAA 20. Alternatively, if you have access to a satellite dish, you can get the data in your AWIPS in about 30 minutes. The nice thing about NUCAPS data is that the timing is such that you get thermodynamic information halfway between the synoptic sounding times, so around 6Z and around 18Z. Why do you want to use this? Wouldn't you rather have an atmospheric sounding in southeast Colorado here rather than relying on model data? The vertical profiles are produced with a two-step method. First, a statistical regression that uses static coefficients that were derived from 4 focus days are used to create a first guess field that is also used for cloud clearing. Then a retrieval is used that minimizes an observation minus calculation value. The regression uses all channels. The retrieval uses a subset of channels. The retrieval is shape preserving and adjusts the regression to a solution. The retrieval is done using a radiative transfer model that has 100 standard levels. That's more levels than are warranted by the sounder resolution, but you'll see all 100 levels in AWIPS. The effective vertical resolution of these profiles isn't big. About 6 to 10 layers of temperature are resolved in the troposphere, and about 4 to 6 layers of moisture are resolved in the troposphere. Keep that in mind when you're looking at the data. About 1/4 of the channels are used in the retrieval. Channels that are chosen are most sensitive to one gas and relatively unsensitive to other gases. This figure also shows in color the wave numbers used to identify each particular gas. Clouds cause problems with satellite-based soundings, and the biggest problem is uniform clouds. As shown at the bottom, NUCAPS does not retrieve thermodynamic environment through clouds. So if you have a uniform cloud cover, that's a problem. But if you have non-uniformity to your clouds, NUCAPS is able to retrieve around the clouds. 9 CRIS fields of regard comprise each NUCAPS dot, and 1 ATMS footprint sits over those 9 CRIS fields of regard. That's the kind of data that's going into each NUCAPS profile. NUCAPS profiles are found underneath the Satellite tab in your AWIPS. Underneath the Satellite tab, you'll see SUMI NPP and NOAA 20. And if you click on that, you'll see NUCAPS sounding availability and also Gridded NUCAPS. When you click on NUCAPS sounding profiles, you'll see something that looks like this, with green dots, yellow dots, and red dots in a swath. Of course, if you're on the East Coast, this swath would be between 6 and 7Z. We're looking on the West Coast where it's closer to 920Z. The dot color means something. Green dots, both microwave and infrared retrievals have completed successfully. That is to say, they converge to a solution. For yellow dots, the infrared retrieval has failed, but the microwave retrieval has not. For the red dots, both the infrared and the micro retrievals have failed. That's a lot of data to scan through. You can use pop-up QTs to speed that process a little bit. So after you load the soundings, enable pop-up QT in the volume browsers, right-click anywhere on the image and choose NUCAPS and turn on sampling, and then when you move around, each time you pass over a point, you'll see the small QT show up. So this is nice if you want to scan for a particular value or see if you can identify a boundary. NUCAPS profiles are useful in the afternoon as daytime convection is just starting to initiate. So in this case over the Midwest, we have a swath of NUCAPS points just to the east of some developing convection in northern Wisconsin. If you compare the two soundings here, you'll notice some differences between the northern and the southern, and that might give you some clues on whether or not this developing convection is going to extend to the south. When you live up north, you will occasionally get sequential passes. So in this case, we had a pass at 17Z, and you'll notice you're right at the western edge of this swath. The next pass had NUCAPS soundings in about the same location. And again, you can use the swath of soundings to make an estimation on whether or not the convection is going to build to the south. Here's another example of consecutive passes over Pennsylvania. So we have a 17Z and an 1830 pass over Pennsylvania. And this was a case on a slight risk day. You had two profiles 90 minutes apart, and we do see some changes in the strength of the inversion, for example, between 17Z and 1830Z. Now you won't see those in South Carolina. You're too far south. But if you had SUMI NPP, you would have two consecutive passes offset by about 50 minutes. And as I say, work is underway to allow you to get SUMI NPP NUCAPS via an LDM feed, where you'd have on the right from SUMI NPP data from around 18Z, and then from NOAA 20 you have data from 1845Z. I want to draw your attention back to these soundings and notice how smooth they are. Again, don't expect to see thin layers or sharp gradients in the vertical. NUCAPS profiles have been demonstrated at HWT, the Hazardous Weather Test Bed, for several years now, and there's generally been favorable feedback. If you click the link, you'll see some blog posts from the HWT blog specifically related to NUCAPS. One thing you'll note when you use NUCAPS sometimes is that the surface values don't match nearby METARs. So that means you need to edit them. So I want to draw your focus to this point near Jacksonville. Note the temperature and the dew point, 73 and 60. And if we look at the NUCAPS profile for that point, do surface values match the observations? And they don't necessarily, so you need to edit things. And there are a couple of different ways to do that. If you click on Edit Data, that brings up a window where you can edit the selected level. So I could change, for example, the 1013.9476, the surface pressure, to something that's more in line with 73 and 60, 22.7 and 15.6 Celsius. Or I can toggle Edit Graph to On. And when you do that, points appear that you can drag around. So I can drag around the points at the surface and near the surface to match the observations at the surface. And then you toggle that back to off, and you have two different soundings. The one on the right is the original, the one on the left is the modified, and you'll see how convective parameters have changed. All I did was change this temperature and dew point at a few of the lower levels to match the observations, and I get a more representative thermodynamic profile. This is the first, I'll call it classic example of how to use NUCAPS data. It came from Dan Neatfeld, who was then the SU in Omaha. Here we have visible imagery with a scattered cumulus deck, and you'll notice that the GFS is predicting precipitation. Wouldn't it be nice to have a sounding here to say, okay, Is this convection going to develop into something that precipitates? And there were NUCAPS soundings on that day. That's shown here. This is a sounding from near Omaha. And if you're looking at the sounding and asking yourself, would I expect convection from this? The answer is probably no. And nothing happened. Several days later, Omaha was in a high risk. We're going to look at the NUCAPS sounding that's in the green box, but I also want to call your attention to the dew point gradient here. 56 at the northern station, 66 and 68 a little bit farther south. Here we have the modified NUCAPS sounding, so it was modified to match the METAR observations of 83 and 63, and it gave a surface-based CAPE in this region of around 1900. We just looked at the NUCAPS sounding in the green box, but there's one just to the south, and given the dew point gradient and the greater moisture to the south, it might be natural to look just to the south to see how the stability is changing. So again, here we have observations showing that nice dew point gradient. We looked at the sounding in the green box, and now we're going to look at the sounding in the red circle just to the south. Here we have that unmodified sounding. Even unmodified, it has a surface-based CAPE of 686, but the temperature and the dew point do not match nearby observations. If we change it, you see a surface-based CAPE now of over 3000. This is going to inform your decision-making about the gradient in moisture, the gradient in stability, and where the thunderstorms are more likely to be severe. Within the last year, gridded NUCAPS fields have been created. The data in the vertical profiles are converted to horizontal fields. I've already showed you where gridded NUCAPS can be found in the AWIPS menu. If you look in the product browser, however, you'll see many more thermodynamic variables available that are derived from NUCAPS. Some of them are listed here. For example, here's a gridded temperature field, and it's the binary probability of the temperature less than 0 at 950 millibars. This was from a day with snowfall in North and South Carolina. So you notice around the tidewater is where the binary probability is greatest. You can also look at temperatures at various levels. So here we have a gridded temperature at 850, 900, and 950 for this same day. I've changed the default enhancement here so that 0 Celsius is black. I put this in a procedure so it's easy to call up. I suggest you do something similar. This was great for determining where exactly the rain or snow might have occurred on this day. Keep in mind that the gridded soundings use all the points, the green, the yellow, and the red. It's up to you, the forecaster, to do some quality control on that. This is the 850 millibar dew point temperature from NUCAPS, and we're comparing that to the NAM and to the RAP. They show pretty good agreements. You can use gridded NUCAPS with convection. Gridded NUCAPS here show totals indices greater than 50 just to the southwest of a tornadic storm that moved through Nashville just before NOAA 20 overflew Tennessee. Here's another example with lapse rates over the Pacific Ocean, and if you look at the night fog brightness temperature difference there and compare the two, as expected, where you have the low clouds, the stable region. Here's a list, not exhaustive, that shows you some examples of when you might want to use NUCAPS in the forecast process. I'm sure you can think of others. This page contains some useful links that you can use to explore NUCAPS outside the AWIPS environment. Check them out. NUCAPS profiles are an independent data source. It's coming strictly from the satellite data, the infrared sounder and the microwave sounder. It excels at identifying gradients, seeing how things are changing, and it has a useful time as well. It's halfway between synoptic sounding times. I hope you have found this training useful. Thanks for listening.